Hello everyone, myself Dr. Santome Kundu. I welcome you all to this lecture of soft computing techniques. This is the fourth lecture of module 12. So in the last class, we have understood some intelligent systems and also the introduction part of Neuro-Fuzzy system. In this class, we will try to understand adaptive Neuro-Fuzzy system, that is NFIS. So adaptive Neuro-Fuzzy systems, NFIS, are a type of hybrid intelligent system that merges the strengths of both neural networks and fuzzy logic. The combination of these two approaches helps to model complex systems more effectively by leveraging in interpretability of fuzzy logic and the learning capabilities of neural networks. The core idea behind NFIS is to use fuzzy inference systems to represent human-like reasoning processes while using neural networks to adapt the systems to new data, improving the system accuracy and decision making ability. Here is more detailed breakdown of how NFIS works. So, first one is that fuzzy logic systems. A fuzzy logic system works with degrees of truth rather than binary true false values. In classical binary logic, truth values are either 0 or 1. You can assume 0 as false and 1 as true. Whereas fuzzy logic allows truth values to range from 0 to 1, which is more aligned with human reasoning. This flexibility helps fuzzy systems handle uncertain or imprecise information. Fuzzy sets are used to model vague concepts or categories where each element in the set has a membership value between 0 and 1. For instance, temperature might be classified as high or low, but fuzzy logic allows a temperature of 70 degrees Fahrenheit to have partial membership in both high and low categories rather than being strict one or the other. Fuzzy rules Fuzzy logic uses if-then rules to describe relationship between variables. These rules mimic human reasoning and can accommodate uncertain or imprecise inputs. An example of fuzzy rule could be if temperature is high and humidity is low, then fan speed is fast. Such rules are able to handle inputs that are not exactly defined, making the ideal for real world problems. Second is the neural networks. So, neural networks are computational models inspired by the human brain. They consist of layers of interconnecting nodes or neurons, each of which processes input data. Neural networks are capable of learning from data, identifying patterns, and making prediction based on those patterns. Structure: a typical neural network consists of an input layer, one or more hidden layers, and an output layer. Each connection between nodes has an associated weight, and the output of each neuron is a function of the weighted inputs it receives, usually followed by an activation function. Training neural networks are trained using algorithms like backpropagation, which adjust the weights between neurons based on the error in the network's output. This training process allows the network to generalize from data and make accurate prediction on new unseen inputs. Combined neural networks and fuzzy systems, ANFIS, that is NFIS, NFIS architecture. NFIS integrates fuzzy logic and neural networks by using the structure of a fuzzy inference systems, but with the added ability to learn and optimize the fuzzy rules through a neural network approach. It adjusts the fuzzy rules and parameters based on input output data using a hybrid learning method. This allows NFIS to optimize the fuzzy system to better approximate real-world systems. The architecture of an NFIS system typically consists of 5 layers, each serving a specific function in the fuzzy inference process. So layer 1 is fuzzification, also known as premise layer. This layer defines membership functions for the input data. The input values are fuzzified, meaning they are transformed into degrees of membership in various fuzzy sets such as low, medium, and high. Each node in this layer corresponds to a fuzzy set, and the output is the degree of membership of the input to that set. Rule is rule evaluation or rule layer. In this layer, fuzzy rules are evaluated. Each node applies an AND operator or any other logic operator to combine the fuzzy fat inputs from layer 1 and compute the firing strength of the fuzzy rule. The firing strength represents how much the rules applies to the current inputs. Rule 3 is normalization or normalization layer. The outputs from layer 2 are normalized by dividing the firing strength of each rule by the sum of all firing strengths. That is Wi bar equal to Wi by summation of Wi. This normalization process ensures that the output of each rule is proportional to its firing strength. The goal is here to make the output values behave like probabilities, ensuring consistency across all rules. Layer 4 is defuzzification or consequent layer. In this layer, the consequent parameters are calculated. The consequent parameters determine the output of the fuzzy rule, typically in the form of linear equations. The output is weighted by the normalized firing strengths from layer 3 and is typically computed as a linear combination of the fuzzy rules consequent parameters. Layer 5, the output layer. This is the final layer which produces the overall output of the system. It computes the sum of the output from layer 4 to generate a single Krebs value that represents the system's final decision or prediction. So this is the typical NFIS structure. So this is the basically structure of NFIS. So structure of NFIS. So that is layer 1, layer 2, layer 3, layer 4, layer 5. So here input x and y. So this is the fuzzy sets. So here we'll get some output that is mu a I x for each rules. Then layer 2 is some operations. So that we'll get for this here you will get mu 1x and mu a 3x. Here you will get mu a 2x and mu a4x, and this is some operator, maybe AND operator or any other operator. So that is the purpose of layer 2. In layer 3, we'll get the normalization value. So we'll get Wi bar equal to Wi by W1 plus W2. In this case, you will get W1 bar equal to W1 by W1 plus W2. That W2 bar equal to W2 divided by W1 plus W2. So this is W2. So in the layer 4, you will get the consequent layer. So that is W1 bar F1 equal to W1 bar F1 is P1x plus Q1y plus R1, and W2 F2 is P2x plus Q2y plus R2. So that is known as Sugeno rule. So that is also structure of Sugeno NFIS. In layer 5, we will get summation of Wi bar into Fi. So here it is W1 F1, W1 bar F1 plus W2 bar F2. So this is the output F equal to. So this is structure of NFIS. So here the membership functions can be any appropriate parameterized membership function such as the generalized Bell function. So mu Ax equal to 1 by 1 plus mod of x minus ci by ai whole to the power 2 bi. So here ai, bi, ci is the parameter set. Parameters in this layer are referred to as premise parameters. When the values of the premise parameters are fixed, the overall output can be expressed as a linear combination of the consequent parameters. So that f equal to, you know, that is w1 bar f1 plus w2 bar f2. So this is the w1 bar and that. So if you put the value here, you will get w1 bar f xp1 plus w1 bar yq1, w1 bar r1, w2x bar p2, w2 bar y q2, w2 bar r2. So which is linear in the consequent parameters P1, Q1, R1, P2, Q2 and R2. So goal is that calculating premise parameters and consequent parameters of NFIS. Hybrid learning algorithm consists of two passes, forward pass and backward pass. Forward pass, node outputs go forward until they are 4 and the consequent parameters are identified by the least square methods. Backward pass, the error signal propagate backward and the premise parameters are updated by gradient descent method. Now training the system. Training process, NFIS uses a hybrid learning algorithm that combines back propagations for optimizing the premise parameters, the fuzzy membership function, and least square estimation for optimize the consequent parameters. This hybrid approach allows the system to adjust the fuzzy rules and membership functions to better fit the provided input output data. Gradient descent. During the training process, the neural network adjusts the parameters, membership functions, and fuzzy rules using gradient descents and other optimization technique. The goal is to minimize the error between the predicted output and the actual output, thereby improving the system performance. Applications. NFIS is versatile and can be applied to various domains where traditional systems may struggle. Some common applications of NFIS include control systems. NFIS is used for adaptive control in complex processes such as robotics, manufacturing, and HVAC systems. It can optimize control strategies in dynamic and uncertain environments. Pattern recognition. NFIS can be applied to classification tasks such as handwriting recognition, speech recognition, and image processing. By combining fuzzy logic interpretability with neural network learning capabilities, NFIS can provide robust recognition systems. Next is the forecasting. NFIS has been applied to predict time series data, including applications in financial forecasting, as for example, stock prices, weather forecasting, and demand forecasting in supply chain management. Modeling complex systems, NFIS is effective in modeling systems that exhibit nonlinearity and uncertainty, such as environmental systems, biological systems, and other real-world processes that cannot be easily modeled using traditional methods. Key advantage of NFIS, NFIS can learn from data, making it adaptability to changing environments. As more data becomes available, the system can refine its fuzzy rules and parameters to improve performance. Next one is that interpretability. One of the key advantages of NFIS is that it maintains the interpretability of fuzzy logic systems. The resulting fuzzy rules are easy to understand, which can be crucial in fields where explaining the reasoning behind decisions is important. Handling uncertainty. NFIS is particularly effective at dealing with uncertainty, vagueness, and imprecision in data. By combining fuzzy logic and neural networks, NFIS can make decisions even when data is incomplete or noisy. So there is one example where we calculate only the output. So in this example, the rule 1 is that if x is small, that is a1, and y is small, that is b1, then f1 is small. So here f1 is given as 0.x into 0.1 y into 0.1, and if x is large, that is a2, and y is large, that is b2, then f2 is given as 10x plus 10y plus 10. Given that a trained fuzzy system above and input values of x equal to 3 and y equal to 4, just find the output of Sugan fuzzy system. That's the values given as Sugan, you know. So here the question x equal to 3, y equal to 4. So first you can calculate the mu ax. So in the place of x put 3. So you will get 3 minus 1, that is 2 minus 2, that 2 by 2 means 1 whole square. So 1 by 1 plus 1, so you will get 1 by 2, 0.5. Similarly, put here x equal to 3, so 1 by 1 plus 3, so that is 3 whole square, 10, 1 by 1 plus 10, that is equal to 0.1. So if you put y equal to 4 here, if you put y equal to 4, so 4 minus 2, that is 2 by 2, 1. So 1 by 1 plus 1, so that is 1 by 2. Again, you will get 0.5. If you put it 1 by 10 minus 4, so that is 5. So 25. So 1 by 1 plus 25, so 1 by 26, that is 0.038. And here if you calculate the value, so f1 may be 0.1 into 3 plus 0.1 into 4 plus 0.1, so I think we'll get it 0.8. And f2 also you'll get 10 into 3 plus 10 into 4 plus 10, so you'll get 80. So these are the calculations. So now, so that is A1 fuzzy set, this is A2 fuzzy set, it is B1 fuzzy set, B2 fuzzy set. So here x equal to 3 given, so 3 here, so membership value something 0.1. For A1 it is 0.5, for B1 it is 0.5, for B2 it is 0.38, so it is 0.038. Now we consider the product operation at layer 2. So consider product operations here. So this is x3, so mu x mu a1 3 equal to 0.5 into here also mu b1 y, this is also 0.5, so take the product, you will get 0.25. Here the product mu a23 mu b24, that is 0.038, so product is 0.038. Now here w1 bar will be 0.25 by summation of 0.25 plus 0.0038, you will get w1 bar is 0.985. Similarly, W2 bar equal to 0.0038 divided by 0.25 plus 0.0038, you will get 0.015. So this is the N1, W1 bar is 0.985 and W2 bar equal to 0.15. So this is basically layer 4. So here W1 F1 is 0.985 into 0.8, so that is 0.788. Here it is W2 bar F2 is equal to 0.015 into 80, so you'll get 1.2. So this is 0.7877 and 0.12. So in layer 5 is summation layer, so you will get the value output is 1.9877. So we are doing the same questions. Earlier we have used the product, now here we are using the T-norm operators. We are using the T-norm or you and operator, you can write the minimum operators. So here the same way 0.5, 0.5, minimum is 0.5, 0.1, 0.3, minimum is 0.038. Now you find W1 bar, that is 0.5 divided by 0.5 plus 0.038, you will get 0.9294, and W2 bar is 0.038 by 0.5 into 0.038, so that is 0.0706. Now we need to go for layer 4, there is the consequent layer. So in the layer 4, that is W1 bar is this, W2 bar is 0.0706, so W1 bar F1 is 0.9294 into 0.3, 0.1 into 3, 0.4, 1 into 4 plus 0.1, so we'll get 0.7435. So actually this is the formula, W1 bar F1 equal to W1 bar P1x plus Q1y plus R1, that is given at F1 is given 0.1x plus 0.11y plus 0.1, and this is the W1 bar, so that is 0.035. Here also it is given F2 equal to 10x plus 10y plus 10, x equal to 3, y equal to 4, so that is 10 into 3, 30 plus 10 into 4 plus 10, so that is 80. So you'll get uh, W2 bar F1 is 0 equal to 5.648. Now layer, we need to move for layer 5. So layer 5 is the summation, so 0.7335, so the output equal to 0.7435 plus 5.648. If you add this two, you will get it 6.3915. to add it, you'll get it. Just add it, or 6.15. So 5.648 here it is. Okay. So if you add it, you will get this thing. So this is the answer. So in this class, we have understood the NFI structures and how to work NFI. So we have understood NFI structure, have understood NFI systems or NFI structure and working procedure. This class you understood these things. So question is today's class. So in the last questions we have took input as x equal to 3, y equal to 4. So you can take solve the given numerical with some other input. As for example, you can take x equal to 9 and y equal to 14 and try to solve the questions. So these are the reference of today's class. Thank you.